Welcome back to the deep dive. You've brought us an excellent stack of sources for this, and I think we're ready to put on our hard hats and get physical.
We have to. If our last conversation was all about the abstract, the bits and bytes.
The digital magic, yeah.
Exactly. Today we have to ground that magic in something you can actually hold in your hand.
Something tangible.
It's the essential follow-up. I mean, we mapped out the magic, but every wizard needs a wand. Magic needs a physical conduit, a source of power.
And our mission for this deep dive is to zoom right in on that. On hardware, the actual components that make everything happen.
The heavy engineering. It's the foundational layer that gives every single digital command its physical form.
I really like how the sources frame this. They say hardware isn't as hard as it sounds.
It's a great way to put it.
And that's exactly our approach today. We're going to try and demystify the chips, the circuits, all those connections, and explain why they're not just, a box of parts.
They're critical functional units, and that core distinction we talked about before, it's still paramount.
The hardware versus the software.
Right. Hardware is all the physical stuff, the metal, the silicon, the plastic you see inside and outside the case. It is the machine.
And the software is just the set of instructions.
The recipe, the thought process telling the machine what it should be doing.
So if software is the blueprint for a house, the hardware is, well, it's everything else. The construction crew, the crane, the lumber, the concrete.
Perfect. Without those physical resources, the most brilliant architectural plan is it's just ink on paper. It can't do anything.
It stays an idea.
Exactly. Hardware is the sturdy bricks and beams of our digital castle. A computer full of incredible software, but with no hardware, is completely inert.
It's that wizard without a wand.
Full of potential, but totally unable to cast a single useful spell.
And when we talk about those bricks and beams, I mean, the speed of their evolution is just, it's astounding. It's a great place to start.
It's a real testament to just how fast this technology has moved.
Just think about the device you're listening to us on right now. What were its ancestors like?
Not very portable.
Not at all. The very first electronic computers were massive. I mean, machines the size of an entire room. They weigh tons.
And needed their own cooling systems, dedicated power, a whole team of people in lab coats just to perform calculations.
Calculations your digital watch can now do in an instant.
It's true. They were huge consumers of space and energy, yet their actual computational power was, by our standards, tiny.
They were glacial. But now, you contrast that with the smartphone in your hand.
Night and day.
Today's hardware packs so much more power, more speed, more memory. It's orders of magnitude beyond those room-sized giants. Talk about a glow-up.
And that scale shift, that miniaturization, is really the silent success story of modern engineering. It's what makes all of this possible.
So how do we make sense of all these modern parts?
Well, the best way is to approach them systematically. And the human body analogy from our sources is, I think, really powerful for that.
Okay, let's unpack that. So thinking of the computer as a human body.
Right. It helps us avoid getting lost in all the technical jargon. It immediately connects the function of a part to its form.
So this is our map for the dive.
This is our map. If you know what the parts of the body do, you can instantly grasp what the hardware is for. The CPU is the brain.
Okay.
The motherboard is the skeleton. RAM is your short-term memory. Storage is your long-term memory.
The heart.
That's the power supply. And then all the peripherals, your screen, your keyboard, those are the limbs and senses, the way it interacts with the world.
And this map really shows you that hardware is a system, right? If the skeleton, the motherboard, is cracked,
Whole system suffers.
or if the heart, the power supply, fails, it doesn't matter how smart the brain is.
The whole body shuts down. It's all interconnected.
Okay, so let's dive into that core architecture. The brain, the backbone, and the heart.
Let's start right in the engine room.
With the king of the castle, the ultimate decision maker,
Yeah.
the CPU, the central processing unit.
Right. This is where all the complex thinking, all the mathematical heavy lifting really happens.
The definition is simple. It handles calculations and instructions, but it's the scale of it that's just mind-boggling.
We call it the brain for a reason. It gets input, it processes that input, and then it sends out instructions for every other part of the system.
So it takes those ones and neos we talked about last time,
The bits and bytes, yes.
and it crunches them. But what does that actually mean? It's more than just being a math whiz on steroids. How does it do the math?
That's a great question. So modern CPUs use something called an instruction set architecture, or ISA.
A language.
It's the native language the chip speaks. You've probably heard of them by 86, or ARM, which is in most phones.
Okay.
When software runs, your computer is basically translating its high-level language, like Python or C++A, down into these low-level CPU instructions.
And the CPU doesn't just do one of those at a time, right?
Not even close. It uses what's called a pipeline. It's like an assembly line. It breaks each instruction down into stages. Fetch it, decode it, execute the math, write back the result.
So while it's executing one instruction, it's already fetching the next one and decoding the one after that.
Exactly. You can have multiple instructions all in different stages of the pipeline at the same time. That, plus a technique called branch prediction.
Where it guesses what's coming next.
It literally guesses the next steps the software will probably take. That combination of pipelining and prediction is how it can execute billions of calculations every single second. It's about being efficient and thinking ahead.
That idea of anticipation is so important. So if we take Mia from Mexico, she's streaming cartoons while doing her homework.
A classic multitasking scenario.
The CPU is managing both of those. It's predicting what video data she'll need next to keep the cartoon smooth, while also prioritizing the letters she's typing for her homework.
And the reason her experience is seamless, the reason the video doesn't stutter, is because those pipelines are working in perfect unison, juggling those different instruction sets. A slow CPU, or one without that prediction, it would all just freeze up.
And to help it go even faster, it has its own little private memory.
Yes, this is a critical detail. It's called cache memory.
Okay.
Cache is built right onto the CPU chip itself, and it is orders of magnitude faster than the main system memory.
So it's like a little notepad right next to the brain.
A perfect way to think of it. And it's tiered, L1, L2, L3. L1 is the smallest and fastest, and it holds the data the CPU needs right now.
So it checks there first.
Always. If it's there, access is instant. If not, it checks L2, then L3, and only then does it go out to the main system RAM, which is much slower, the more it finds in the cache.
The less time it spends waiting.
And the faster the whole system feels. It's all about minimizing that wait time. That sheer speed, billions of calculations per second, is what's needed to feed modern software.
Right, to render a video or a complex game.
At 60 frames per second, the CPU and its partner, the GPU, are updating millions of data points 60 times every single second.
If you tried to count that high.
You'd be an old-timer long before you finish.
Okay, so the brain is settled. It's processing at these incredible speeds using pipelines and cache. So where does this brain live, and how does it talk to the rest of the body?
Which brings us to the structure that holds it all together. The motherboard.
The central nervous system.
That's a great way to put it. It's that main big circuit board you see inside the case, and every single piece of hardware, the CPU, the RAM, your storage drive, it all has to connect directly to it.
So sticking to our body model, this is the backbone or the skeleton.
Yes, it provides the physical structure, absolutely, but its real job is communication. It's the communication hub.
And all those little lines you see etched on it.
Those are the pathways. Microscopic traces of copper that let electrical signals travel between all the components at incredible speeds.
Without it, the CPU is just an island.
An isolated genius. It needs those pathways to send its instructions out. And for anyone really studying this, you have to understand that the speed of those pathways is often controlled by the motherboard's chipset.
Okay, now this is a technical detail that often gets missed. The chipset.
Right. It's the traffic cop for the whole system. It used to be two chips, the North Bridge and South Bridge.
What'd they do?
The North Bridge handled the super fast traffic, communication between the CPU, the RAM, and the graphics card. The South Bridge handled all the slower stuff, like your USB ports and hard drives. Now it's mostly integrated into one chip.
And the quality of the motherboard determines the speed of those connections, the buses.
Absolutely. You can have the fastest CPU in the world, but if you put it on a motherboard with slow bus speeds, you've created a bottleneck.
It's like putting a Formula One engine in a pickup truck.
Exactly. The data just can't get where it needs to go fast enough to keep that powerful CPU fed with instructions.
The motherboard also has that little battery on it. What's that for?
That powers the BIOS UEFI. It's the basic firmware, the first little piece of software that wakes up when you press the power button.
Before the operating system even loads.
Way before. It runs a check to make sure all the hardware is there and working correctly, and then it tells the storage drive to load the operating system.
The sources have that great try this at home activity. Safely opening up an old, unplugged computer.
I highly recommend it. When you look inside, you'll see that big green or brown board, and you'll see the physical slots for the RAM, the socket for the CPU.
All those different colors and shapes.
And each one is a specific interface, a dedicated lane for talking to the central chipset.
And when you think about Raj in India using his smartphone for gaming, That's a motherboard too, isn't it? Just a tiny one.
It's a marvel of engineering. All those functions, all those high-speed pathways are squeezed onto a tiny piece of silicon. The challenge isn't just size. It's managing the heat and making sure the signals don't interfere with each other in such a confined space.
So the motherboard provides the structure, the communication network, but none of it works without power.
Which brings us to the life source, the heart of the system, the power supply unit, or PSU.
The unsung hero, always tucked away in a corner.
But absolutely critical. It performs a vital conversion. The power from your wall outlet is alternating current, AC. It's high voltage, and electronically speaking, it's very messy.
And the components inside the computer need something different.
They need very precise, low voltage, direct current, DC. The PSU takes that messy AC power from the wall and converts it into the clean, regulated DC power that the CPU, motherboard, and everything else needs to survive.
So it's not just a power cord, it's a regulator.
It's a regulator and a transformer, just like a heart-pumping, clean, oxygenated blood to every part of the body. If the PSU is faulty and sends out dirty power, it can literally fry the other components.
That's why you see those numbers on them, the wattage.
Right. The wattage is the total power budget for the system. If you have a powerful CPU and a really beefy graphics card for gaming, you need a high wattage PSU to make sure they both have enough power to run at their peak at the same time.
And what about those efficiency ratings? Like 80 plus bronze or gold?
That's a measure of how effectively the PSU converts the AC power to DC. A lot of power can be lost as heat during that conversion.
So a more efficient one wastes less electricity.
Wastes less electricity and generates less heat. An 80 plus gold PSU is more efficient than a bronze one, meaning it runs cooler and quieter and puts less strain on your electric bill.
So when you hear that fan whirring away, that mini tornado sound.
A lot of that can be the PSU's fan working hard to get rid of the waste heat generated during that power conversion.
Okay, so we have a functional body, a brain, a skeleton, and a heart. They're all powered up and stable.
Now we can move on to the more specialized units.
Let's do it. Section 2, memory, storage, and visuals. These parts are all about speed, persistence, and sight.
And we have to start with pure speed. RAM, random access memory.
This is the computer's temporary workspace.
The lightning-fast workspace, yes. It holds all the data for whatever the computer's doing right now. The browser tabs you have open, the document you're editing, the game you're playing.
And its key feature is that it's volatile.
It's volatile, which means if the power goes out, even for a split second, poof, everything in RAM is gone. Wiped clean.
It forgets everything.
It's electronic, not magnetic like an old hard drive, so it needs constant power to hold on to its data.
It really is the ultimate short-term memory. It's like remembering a phone number just long enough to dial it.
That's a perfect analogy. You hold it in your head for 30 seconds, and as soon as you've used it, it fades away. Unless you write it down.
And writing it down is saving it to long-term storage.
Precisely. And we've all learned that the hard way, forgetting to hit save on a big document and then the power flickers.
It's a painful lesson.
Yeah.
So this speed is essential. The CPU needs the RAM to be fast.
It's crucial. We talked about the CPU's cache being the fastest memory. Well, RAM is the next level down in that hierarchy. The CPU is constantly pulling data from RAM to work on. If the RAM is slow, the CPU just sits there, waiting. It creates a system bottleneck.
And that's why having more RAM lets you do more things at once.
Yes. More RAM means a computer can juggle more tasks without getting bogged down. It's like having extra hands. If you're trying to edit a video with 50 browser tabs open for research and you're listening to music,
You're using a lot of RAM.
you are asking the RAM to hold 3 very large, complex workspaces open at the same time. The more you have, the smoother that experience is.
And the newer types of RAM, like DDR5, are just faster at that transfer.
They offer much higher clock speeds and more bandwidth. That means data can move between the CPU and the RAM sticks more quickly, which translates directly into how responsive your applications feel. It's all about minimizing that lag.
Okay, so that's the immediate temporary workspace.
Right.
Now let's talk about the library, the permanent record.
Component 5, storage long-term persistence.
This is where everything lives. Your operating system, your photos, your apps.
It's the computer's long-term memory. Remembering your favorite song lyrics from 10 years ago, it's always there, ready to be recalled.
And the sources point out this massive shift in technology here, from the old spinning disks to the new solid-state drives.
This has been one of the biggest performance game changers in the last decade. The old HDD, the hard disk drive, was mechanical. It had spinning magnetic platters and a little arm that had to physically move to find the data.
And that physical movement takes time.
Milliseconds, but it adds up very, very quickly. It's called latency. The system is just waiting for the drive to spin up and for the arm to find the right spot.
And you could hear it. That little hum or click, the sources call a tiny helicopter taking off.
That was the sound of mechanical action. But the SSD, the solid-state drive, changed all of that. It has no moving parts.
It's all electronic.
It uses flash memory chips. They're like RAM, but they're non-volatile, so they hold onto their data even when the power is off. Since there's no movement, accessing data is nearly instantaneous.
The difference in speed is it's not even close.
It's astonishing. Booting up your computer used to take a minute or more. Loading a big game could take several minutes. On a modern SSD, those same tasks take just a few seconds.
And not all SSDs are the same, are they? There's another level to this.
You're right. It also depends on the interface, how it connects to the motherboard. You have the old SATA interface, which has its own speed limit.
Okay.
But the newest SSDs use a standard called NVMe, and they plug directly into the motherboard's fastest communication lanes, the PCI Express lanes.
The ones we talked about the North Bridge managing before, the superhighway.
That's the one. An NVMe drive can communicate with the CPU at staggering speeds, maybe 5 or 10 times faster than an older SATA drive. It's another leap forward.
And the reliability of this long-term storage is so important. When you think of Aisha from Kenya saving her school project on her tablet,
She is completely relying on that non-volatile hardware. She needs to know, with absolute certainty, that her work will still be there tomorrow when she opens it again, regardless of the battery level. That hardware integrity is what makes her digital schoolwork possible.
we've covered thought and memory. Now we need to cover sight. The ability to actually see what the computer is doing.
Component 6. The GPU. The Artisan Vision Specialist.
The graphics processing unit.
Right. If the CPU is the general manager of the whole company, the GPU is a highly specialized artist focused entirely on one thing, calculating graphics.
It turns all that data into the pixels you see on your screen.
The CPU could do that work, but it would be incredibly inefficient and slow. The GPU is designed from the ground up for this specific task. If the CPU is the brain, the GPU is the specialized eyes and hands for drawing.
How is it designed so differently?
It all comes down to serial versus parallel processing. A CPU is built for serial work. It has a few very powerful, very smart cores that are designed to do one complex task after another very quickly.
Okay, one thing at a time, but super fast.
Exactly. A GPU is the opposite. It's built for parallel work. It doesn't have a few smart cores. It has hundreds or even thousands of smaller, simpler cores that all work at the same time.
So it's not one genius, it's a giant team of specialists.
A perfect analogy. Imagine you need to paint a giant wall. The CPU is one master painter who can paint the whole wall very quickly, stroke by stroke. The GPU is 1,000 painters who each take one tiny square of the wall, and they all paint their square at the exact same moment.
And a wall gets painted instantly.
Because rendering graphics is a naturally parallel task. To show an image on your screen, the computer has to calculate the color and shading for every single pixel.
Millions of them.
Millions of tiny, independent calculations. The GPU just assigns a few of those pixel calculations to each of its thousands of cores, and the whole image gets generated simultaneously. That's how you get smooth video and high frame rates in games.
And that's why gamers, like Liam from Australia and the sources, depend so heavily on a good GPU.
Absolutely. To see those crystal clear dragons in a 3D world, the software's instructions have to be translated into light on a screen 60, 90, even 144 times every second.
That's the hardware making the software visible. The perfect marriage of the two.
It is. The abstract command becomes a physical reality you can see.
Okay, so we've built the internal body, the core architecture, the memory, the vision. But a body needs to be able to interact with the world around it.
It needs its senses.
Which brings us to Section 3, Interaction and Application, the global gateway.
We're talking about peripherals, all the external bits and pieces that let us, the humans, talk to the machine.
The keyboard, the mouse, the monitor, the speakers.
These are the physical bridges. If the internal parts are the core of the system, the peripherals are the computer's limbs and senses.
The screen is its voice, or its visual sense. The keyboard and mouse are its hands.
And they are constantly translating our physical analog actions into digital signals that the motherboard can understand.
The sources suggest another hands-on activity here. Safely opening up an old keyboard.
It's a great way to visualize it. You see the plastic keys on top.
But underneath, there's a rubber membrane or little mechanical switches.
And when you press a key, all you're doing is physically closing a tiny electrical circuit. That's it.
And that sends a unique signal down the wire.
A unique signal for that specific key. It travels along the motherboard's bus lanes to the chipset, the CPU interprets it, and then the command is executed. Maybe the GPU is told to display a letter on the screen.
So that one satisfying click you feel when you type.
It kicks off a journey through the entire hardware ecosystem we've just described.
And the source mentions the complexity of hitting multiple keys at once.
Right, that's called the key matrix. The hardware has to be designed to correctly identify both signals if you press two keys at the same time, without getting confused. Older hardware sometimes had issues with that, a phenomenon called ghosting.
So let's widen out again. This whole interconnected system of hardware is really the gateway to global application, right? It enables education and connection everywhere.
It's the physical enabler. Let's look at those global examples again and tie them to the specific hardware.
Okay, Sophia from Brazil, researching rainforests for her homework.
Her ability to quickly open a dozen different websites, all full of images and videos, and cross-reference them with PDF documents, that is directly dependent on having enough RAM.
And fast RAM at that.
And a motherboard with high bus speed to move all that data around. The faster her hardware, the less time she spends waiting for pages to load.
The practical result is she gets her work done faster.
Which leaves her with more time for other things, like soccer. The efficiency of the hardware is literally giving her back time in her day.
What about Chen in China, video calling his grandparents?
That's a huge hardware task. It requires a dedicated network interface card to handle the internet connection and then constant coordination between the CPU and GPU.
For what?
To compress his video feed, encode it, send it across the world, and then receive their feed, decompress it, and display it on his screen, all in real time.
And if the hardware is slow, the call stutters and drops.
And the emotional connection is broken. The hardware's speed and reliability are what maintain that human link across thousands of miles.
And the sources also highlight how hardware is a tool for empowerment.
We see inclusivity in action.
Kids in Africa safely modifying tablets to learn how to code.
That shows how robust even basic hardware can be. They're taking these tablets with their small CPUs and running simple compilers and development tools on them. They're repurposing hardware to build new skills.
And the kids in Europe building robots with hardware kits.
They're literally bridging the software-hardware gap. They write code, which is software that tells a microcontroller, a tiny little CPU, to activate a motor or read a sensor, which is hardware. They're learning system design.
And designing apps on family computers in Asia.
That emphasizes that you need a solid combination of hardware to do creative work. You need a decent CPU, enough RAM, and a fast SSD to run the complex development software that's required to build the next great app. You can't do it on a machine that's constantly lagging.
So the main takeaway is clear. Hardware is the physical bedrock that executes all those abstract commands we talked about before.
It connects us, it empowers us, and it provides the tool set for creation and communication no matter where you are in the world.
Okay, we've taken the machine apart and analyzed all the pieces. Now let's put it back together in our minds.
Let's move to Section 4, Conceptualizing and Inventing. We want you to internalize this structure and start thinking like an engineer.
And the best way to do that is to build something.
Exactly. Let's talk about that super fun activity of building a computer out of cardboard.
This isn't just a craft project. It's a mental exercise in architecture.
When you have to physically decide where the motherboard goes, you start to understand the structure. The CPU stops being an abstract idea and becomes a physical chip that needs a specific socket in a specific place.
So let's walk through the steps as a thought experiment. First, you get your boxes and markers.
Step 1, you take the biggest box. That's your case. That's the protective housing that keeps the sensitive parts safe from dust and physical damage.
Step 2, you cut out the shapes for the components. A big square for the motherboard.
The foundation. Then a little chip for the CPU to remind you that the brain is tiny. Some long sticks for the RAM modules. A circle or a rectangle for your storage drive.
And step 3 is the most important part.
You label them all and you tape them onto your cardboard motherboard. And then you add strings to be the wires.
Why are the strings so important?
Because they visually reinforce the fact that all these parts have to be physically connected. Power and data have to travel along those dedicated pathways.
So you can trace a command, Open a file.
You can literally follow the string from the storage disk to the motherboard to the CPU chip, which then uses the RAM sticks to work on it. It makes the abstract flow of data tangible.
And it connects back to our fun fact at the beginning, those giant room-sized computers.
They had the exact same functional architecture, a CPU, memory, storage, all connected. The principles haven't changed in 70 years, only the scale and the speed.
So building the model helps you understand the structure. What's next?
We want to challenge you, the listener, to go one step further, to use that understanding to invent a new hardware gadget.
Apply these components, CPU, RAM, storage, to solve a new problem.
The sources give some really fun conceptual examples, like the homework helper helmet.
Okay, how would that work from a hardware perspective?
Well, to scan a book and explain it, it would need a specialized optical scanner, that's a peripheral. It would need a very fast, very small mini CPU to run the image recognition and natural language processing software.
And what about the global friend finder watch?
That's a storage problem. It would need a massive amount of persistent, non-volatile storage to hold language translation databases. And it would need a very power-efficient CPU and RAM, probably an ARM-based chip, to make the battery last.
So that's the challenge.
That is the expert challenge. Draw your idea. Think about what components it would need. This is how innovation starts. Every piece of hardware we use today began as someone's drawing, someone imagining a new way to arrange these fundamental parts.
This has been an incredible journey. We've really dissected the digital body, from the abstract software down to the physical silicon and copper.
Let's do a quick synthesis. One last time with the body analogy.
Okay. The CPU.
The brain. Billions of calculations a second, using its pipelines and cache.
The motherboard.
The skeleton and nervous system.
Yeah.
The foundation with all the critical communication pathways.
And RAM.
Your short-term memory. The super-fast workspace that lets you juggle multiple tasks at once.
And all this specialized hardware makes our digital lives faster, more fun, and just full of possibilities we couldn't have imagined a generation ago.
It translates those abstract software commands into a visible, usable reality for everyone all over the world.
The foundation is now officially laid. We know the parts and what they do.
Which sets us up perfectly for our next deep dive. Architecture.
The design of the system.
It's not just knowing the parts exist, it's understanding the blueprint. The science of how you arrange them so the CPU and RAM can talk to each other without any delay or interference.
It's the how, not just the what.
Precisely. So we understand the components. But here is the final provocative thought for you to think about until next time.
Let's hear it.
We talked about data traveling at near light speed across the motherboard along those little copper pathways. That requires timing that is accurate down to the picosecond.
Okay.
So the question is, how did engineers figure out the optimal geometry of those pathways? The exact length, the exact curves, the precise timing.
To make sure a signal sent by the CPU arrives at the RAM at the exact nanosecond it's supposed to.
Without getting scrambled by interference from the massive amount of power being converted by the PSU right next to it. It's a mind-bending challenge of physics and spatial design.
Think about that flow, that perfect microscopic choreography, and we'll meet you back here to discuss the blueprints of architecture next time.
Until then, keep questioning, keep drawing. And remember that underneath every single click, a whole world of intricate hardware is working hard just for you.
Stay curious, explorers. The digital wonderland awaits.